Hi, my name is Nicholas Lange, and this is a pre-recorded presentation for Virtual Mathspsych 2020, and it's based on work I've been doing with Henrik Zingman at the University of Warwick. Now, before I start talking about visual working memory, let's talk a bit about why we bother with modeling in the first place. So the way it usually works is that we have a theory that is instantiated in a particular model, and we fit that model to some data. And there's a competing theory with a competing model. What we then do is compare those models. And the aim of this model comparison is to identify the model that predicts novel data in the best way, because it captures regularities of the data, but also to then draw some inferences on the basis of those models capturing the regularities about the theoretical mechanisms that are actually important. So what we're going to try and do in this work here is to isolate theoretical mechanisms in models of visual working memory that are crucially important in doing a good job at predicting data. Why did we use visual working memory in the first place? Well, it's basically because the models are quite modular, so it's theoretically quite reasonably easy to identify individual theoretical mechanisms. We're using the delayed estimation paradigm and models applied to this paradigm, and this looks something like this. On any given trial, a participant is shown a number of dots on the screen. One of those dots is then randomly probed, and they have to indicate the color of that dot by choosing a color on the color wheel. And the dots on each drive has basically different numbers of dots that are shown. And the kind of data that comes out of that looks something like this. So it's an individual participant's data for all the trials for set size of 1 through to set size of 6. 0 indicates the true color of an item, and so this indicates participants' responses overall and how far they stray from the true color. And what models of visual working memory try to do is essentially fit these error distributions across these set sizes. And the simplest one, as you can imagine, you look at these distributions and say, well, they kind of look like normal distributions. So we use a normal distribution on a circle for Mises distribution. And if we assume that the precision, so kind of the inverse of the spread of the distribution changes with set sizes and fit that to the data, we get something like this. So we get a reasonable fit to the data, can't quite capture the peakiness of the data and can't quite capture the tails, but it kind of works. Now, not that long ago, there's sort of a new class of models sort of came on the scene called variable precision models that assume precision doesn't just change with set size, but it also changes across trials and across items. And if you modify the model and assume that the model becomes a kind of a continuous mixture, you get something like this. So you kind of get a better sense of the peakiness and the tailiness of the error distribution. So we're using this variable precision model as our sort of base model. And what we're interested in is kind of the added features people add to those models to do an even better job at predicting data. And we picked two of them to test whether they're actually necessary in those models. Number one is response noise. So the model that I've talked about so far assumes that when you make a choice on the color wheel, that is actually the correct representation of your memory of that color. Other models assume, well, there's some response noise involved because when you click with a mouse, you might shake a bit, so that there's some noise in your response, literally. So we're comparing models with response noise, without response noise, and then we're interested in whether there's a limit to the memory capacity. So the sort of standard variable precision model assumes that memory is unlimited. So on a given trial, we are shown 8 items, you probe for random 1, your response to that item is going to be based on memory, even if not a lot of memory. The opposite idea is to say, well, memory is limited. You may only remember, say, 5 items on all trials. To mathematically incorporate that, essentially you turn this continuous mixture again into another mixture and add a kind of guessing term here. And the F model, that's sort of the simplest memory capacity limit model, assumes that this memory capacity is stable in participants, so it's fixed across trials and across set sizes and across items. Other models that assume that memory capacity is limited assume, well, that in the mean it's sort of limited to k items, but that again this is based on a sort of underlying distribution, and we're looking at models with 2 different distributions: one that assumes it's Poisson distributed and one that assumes that it's uniformly distributed. And again, you create kind of a mixture of a mixture of a mixture with some weights given by the distribution. So those are the 8 models we fitted to the data, and we're interested in whether response noise matters overall and whether there's sort of limits to memory capacity overall versus unlimited memory capacity. And we fitted these models to 195 individual trial-level data sets, largely collected by Vandenberg for his 2014 paper. We added some of them, And they differ in the sort of critical feature dimension that they test. Some test color, some test orientation, and they differ in the sort of set sizes they test, and they also differ in the overall memory performance. And we fitted those data sets quite a few times. This is kind of where the cross-validation comes in. So we first fitted it in a kind of the conventional way to compare models by AIC. So we estimated the maximum likelihood for all models, penalized it by the number of parameters to kind of approximate generalizability, to identify the models that don't overfit but capture irregularities, don't capture the noise. But then we wanted to see whether cross-validation comes to the same conclusion that tests generalizability directly. So we use specifically tenfold cross-validation, where we split each individual data set into 10 folds, always held out one fold on each fitting run, used these sort of training runs to predict that held out fold, and then summed across the held out folds to get a kind of holdout deviance, so to speak, as a sort of critical term to compare models on. And we made sure that all folds had the same number of trials from all set sizes, because then we also looked at kind of more a specific generalizability to ask, well, can models predict the performance in set sizes we haven't seen yet? So where each fold was defined by all the trials in one set size, and we held out a set size entirely, and then tried to predict performance in those set sizes. So this meant that we actually had quite a lot of numerical effort in fitting all these models, what we did. So what we're interested in, again, is to say, well, do we need response noise, and is memory limited? And if we look at the results by AIC first, we see that overall models with response noise seem to be doing better than models without response noise, but that the differences are actually reasonably small, but that the differences are even smaller when you look within the response noise clusters. Second thing you see is that even though we say U plus model wins in the response noise cluster, the U minus model doesn't win in the no response noise cluster, suggesting that there isn't a clear overall pattern for a specific limit to memory capacity. We thought that maybe cross-validation gives us slightly different results, but it doesn't in this case. So we didn't suddenly have a situation where the simpler models are actually winning. So it does suggest that in this particular case, AIC actually manages to capture generalizability quite well, and that cross-validation doesn't particularly add anything to that. But we also ran the second kind of cross-validation, which is maybe the slightly more interesting one for us, because certainly the results are a bit more interesting. So what we can see here is that overall, that is averaged across all the held out set sizes, models with response noise are massively better than models without response noise. And this is much clearer than in the previous graph. And we were a bit curious as to where exactly that comes from. So we can split up the data by all the held out set sizes, and we get something like this. So what you can see here is that this overall pattern here is basically driven by the pattern for when set size 1 is held out. So the model is trained on all those set sizes and then tries to predict set size 1. And there clearly, models with response noise are much better than models without response noise. This isn't the same case for any of the other set sizes. So here set size 2 is held out, so set size 1 is included in the training one, and actually suddenly you see there's no difference between models anymore. You might say, well, you said that different experiments use different numbers of set sizes, and maybe it's just odd averaging that goes on because it's averaged across all participants, so it's a bit messy. If we only look at the experiments that used all 8 set sizes, we still get the exactly same pattern of data. That basically suggests that set size 1 is really important in distinguishing between models, but that other set sizes aren't, and that adding more and more and more set sizes doesn't actually add anything in sort of predicting data at all. It's not at all necessary. So it's not the case that more data is necessarily better. So what conclusions can we draw preliminarily? Response noise seems to matter. Memory capacity, not really. And if it does, well, the differences are very, very minor. And this is a problem that as we come to trying to draw inferences about the theoretical mechanisms, because while this data looks reasonably clean and you might want to interpret it, actually there's a few issues you might want to consider first. Number one is that there's large differences between data sets. So if we look at the AIC graph and split it out by individual experiments, and let's put it on its side, we see that quite a number of experiments follow the same sort of overall pattern that I've shown before, but there's quite a few experiments that don't actually, that show something completely different. And if you look at the data underlying those experiments, you also see that the sort of trends in those data sets are also different to the overall trends in the data. And this is, great because we have a lot of experiments we can test, but it's problematic because now clearly it's not that overall the U plus model actually is best, but given some weird data or, different data, suddenly it doesn't perform as well. So does it actually, matter overall? The second thing is that the maximum likelihood estimates we used as a basis for all our comparisons are actually very, very unstable. So we ran each model 20 times on each data set. This is the comparison for AIC. And we compared the best run and the second best run of each data set to see how far apart they are in their maximum likelihood estimates, so in deviance terms. And if you say have a threshold of one deviance term where you assume that if models are that close to one another, then the model is, the fit of that model to that data set is quite stable. You see that quite a lot of data sets are unstable in all the models. And you could say, well, just, we can just exclude those particular data sets. Maybe it's just participants being weird. So that's like 13% of data sets, roughly, in quite a few of those models. The problem is if you want to only include data sets that are stable for all models, because you're trying to compare all models at the same time in this kind of exercise, you actually have to exclude more than half of the data sets if you assume a tolerance of one deviance point, and many more if you go down in the sort of tolerance you're happy to accept. Now remember, some of the differences between the models we looked at were actually below this one deviance point. So if models in themselves are that unstable, you can't actually draw any conclusions based on an overall difference between models when the model difference within models is that minimal. And then we also ran parameter recovery and model recovery exercises, and those were also not great. So if you look at model recovery, we generally can recover sort of response noise clusters. But if you look at the sort of proportion of data synthetic generated data sets that are recovered by a particular model, you see that the A model, so that's the one with unlimited memory capacity, actually dominates a recovery massively. Even if you assume, and this is this graph, that if two models fit within one deviance point of one another, they're sort of equally fit and equally preferred. But still, you have clearly this model dominating. You might have like a bit of a diagonal, but it's not as clear as ideally you would like. And there are massive issues with the stability of parameters and with the recovery of parameters that make interpreting parameters, especially when it comes to the capacity limit, sort of memory capacity limit, very, very, very difficult and not great. And it's sort of worse than what I've shown you so far, basically. So what did we learn overall? Well, we learned that the AIC does reasonably well to capture generalizability, which is great. So it does mean that while we obviously want to advocate for cross-validation, it's kind of what we started out with, it doesn't seem to matter as much here. So I think you can probably save that numerical effort, at least when it comes to this kind of general cross-validation. I think the situation is much more interesting when you start being interested in making very specific predictions about, in our case, whether models can predict novel set sizes, or more generally, when you start trying to predict performance of models in other sort of paradigms, for example, using sort of the same metric of like holding out one paradigm. It does suggest here that set size 1 seems to be really interesting, and that adding more data by getting participants to complete even more trials at different set sizes probably doesn't actually add anything. The stability and recovery of the models we've tested is super questionable, which makes interpreting the actual model comparison results really difficult. So you might want to say, well, okay, but the difference between response noise clusters was actually quite clear. The problem is that those models are more unstable than the models that don't incorporate response noise. So now actually you have to make a lot more numerical effort to make sure you get stable results. And it does suggest that we can't say anything about whether memory capacity is limited or unlimited. So whether this is a kind of crucial theoretical mechanism. And finally, what we set out to do is isolate the workings of theoretical mechanisms that are crucially important. But given we can't do that here in comparing very similar models, it's a bit unclear how you would do that when you have models that are globally very different. And that's it. Thanks for watching. And here's some pictures of my dogs and what they usually do when I talk about research.